Recording started successfully. Okay. I'm going to introduce the speakers, Sophia Drossopoulou and James Noble. I've been working with them and also Toby Murray on this body of work now for, what, a couple years. Sophia Drossopoulou is a professor of programming languages at Imperial College. Her current interests are type systems, actors, and reasoning about programming. James is a professor at Victoria University, Wellington, New Zealand. Research, long interest in object design, aliasing, object ownership, design patterns, agile visualizations, and computer music, and yet more stuff. And now I will turn it over to them. Screen share.
This is when there's a flick and then everything suddenly goes black, isn't it?
Yeah.
No, maybe. I can see it.
Excellent. Okay, take it, James. James and Sophia will each be giving part of the talk.
Thank you. So it's 11 o'clock. It's nice to be here. And how long have we been trying to give this talk for? A year, I think Mark said, you should come to Google and talk. And we said, yes, we should. Okay. So reasoning with code of unknown problems. In other words, how do you know what your program's going to do when you don't know what your program is? As Douglas Adams would say, this is, of course, impossible. In mathematics, because we, particularly Sophia, likes all logic, we can model this with, now you see I don't know how to move the thingy with this.
Feel free to use the
use the mouse pad.
Use the trackpad.
You see, because we were told to use the trackpad, use the pointer on the screen for recording. But it's. Does anyone notice any minor problems with this?
Yeah.
I've got this super chunky pointer on your laptop.
And a tiny pointer over there.
Super chunky, like you can't actually see the X on the screen. The pointer is covering it up.
Yeah, I have.
In the room, you could use the thing in your hand and actually point at the screen, but that just doesn't work.
But we were told not to.
Yes.
We were told not to by marking 2 separate emails. Right. So for those of you who can't make out the minuscule pointer, you know, this is a method call. X is the receiver, M is the method, Y is an argument pointed in, and there is this traditional rule of reasoning from Tony Hoare, which lets us calculate, given a specification for the method up here, a precondition and postcondition, what this method call will actually do. Of course, it relies on you, well, knowing what that object is and being willing to believe what the method will do. But what happens if I know nothing about the receiver? What happens if this receiver is a web service? What happens if this receiver is, if I'm a web service and this receiver is some kind of token or cookie that's been handed in by a client? What can I do? Well, basically, this is mathematics for, I am in Google and in America, who the mathematics for Trump knows. Okay, sorry. Sophia is already running her eyes. We don't know. We can't say anything. Anything this does, this says our reasoning system has to assume is true. So absolutely no constraints on it. Well, in this talk, we're going to argue that we can do better than that, and that it's important to do better. So, what research questions are we looking at? These objects do collaborate with other objects of open provenance. If you're lucky, you've thought about this when you're designing your code, and you know that one of the objects, who do I talk to, the camera or the room? I talk to the room. One of the objects is unknown, if you think about it. Or maybe, you know, you're actually just an average web programmer who earns their money not by, you know, pontificating at Google, but by actually having to deliver software for people. And, you know, this code needs to be done by the end of the day, so we just write the code. Maybe we don't even know about that, but you can still get on with business. The important thing is that often in these systems there is no central trusted authority. Okay. Even as far as a company like Google with Google Play or Apple with the App Store goes, and will in some sense sign applications, they're certainly not including or assuming any liability for what those applications might actually do. You can't sue Google. Google doesn't guarantee that everybody who interacts with you on your iPhone is somebody trusted. What this means in practice is that our code really ought to be very robust. And what it means from our research point of view is we need means to specify trust and risk, and we need means to reason about adherence to these specifications of trust and risk. And stepping back one step further, I'd say we actually need good ideas about what it means in these kind of open, diverse computer systems, what trust actually means and what risk actually means. And that's basically what the talk will be about. Our contributions so far are these techniques that you can use in the specification language to give meaning to these ideas, and I'm arguing the concepts that lie behind them. So an obeys predicate says we are willing to accept in writing our code, or at least perhaps to assume when we write our code, that some object will adhere to some specification. We have a may access predicate, which says, well, some object can get access to something. You can think of this very much as like may alias in compiler analysis, if you're used to that. And then again, may affect. Some object may actually affect, may change some other property. These predicates are hypothetical and often used conditionally, and we'll talk about how that goes as the talk proceeds. And then practical practical isn't the right word, solid contributions is a whole logic, a set of reasoning rules that incorporate these predicates to reason about the design of algorithms. And we've picked one example, which is an escrowed exchange, which we'll be using in the talk. Mark has a version of this implemented in JavaScript, and we have a slightly different version. And what we're trying to do is to apply our ideas to this, to talk about what needs to trust what in this example, and then ultimately to argue that, in fact, Mark's design, or a slight variant of that design, can, in fact, meet a specification that it can do what it says that it does. Crucially, that it can do what it says that it does in an open system, where the objects with which it must participate are not necessarily trustworthy. Okay, questions? Feel free to hurl questions or abuse as necessary. Where did we get to? Well, we could write the specification, with which we're inordinately pleased, because people couldn't really write those sort of specifications before. We proved by hand adherence to the specification, and what's interesting is that the specification turned out to be weaker than we and the escrow authors thought. That there were conditions, that there were things that they thought this escrow could achieve, which in fact it couldn't, and Sophia will talk about that later. We don't consider concurrency and distribution and a bunch of other things the code in the ESOP 3 paper does, works correctly. And again, another thing, we will assume that different arguments to our methods aren't aliases, and there are a number of other these sort of conditions. These are simplifying assumptions, not because we don't think these can be handled, or not because we don't think that these issues are important. They're clearly all important. And in these kind of environments these days, these systems are distributed and they are concurrent. What we're trying to do is get at something that's necessary but not sufficient. So if we can't come up with these arguments in the sequential single machine case, then we can't do this in the distributed setting. If we can do this, and we think we now can do this in a sequential case, then in fact what we were talking about an hour ago was, well, what will it take to generalize this to a setting that is concurrent and is distributed? Our research agenda is not constrained to exchanges. The escrow example we're going to talk about is paradigmatic to a family of problems, but in fact there are another wide set of problems that we can talk about that doesn't depend on this escrow. So basically, the remaining talk, I'll talk a bit more about terminology, the open world, and trust and risk, and introduce the escrow agent, and then Sophia will talk and really go deep into the escrow agent and finish up by talking about the whole logic. We promise not to talk about guardian soulmates, but if you're interested, you can ask us afterwards. So, open, trust, and risk. What do we need by an open system? Well, basically, we model open systems through the idea that we can dynamically link any unknown, potentially malicious module M prime. So this is incorporating code that really we don't know anything about. This could be a cookie or an object handed in from somebody else. If we're really unlucky, it might be some library that we just pulled off the net and compiled in. And what we're going to say is we're going to be talking about defining the policies in here. Some module supports or obeys some policy if for any other module M prime and for any program state arising here from this conjunction of M and M prime, which is capturing this idea, here's the code we've written in module M, here's the rest of the world in M prime. What we want to do is combine those things together into a single program, and we will only consider that M adheres to the policy if, in fact, the composition of M with any other module adheres to that policy. So M prime represents the adversary, and then there's this notion of arising, which means we can use the code in the combination of M and M prime, and particularly the code in M, the code that we've written, to constrain the state that the system gets into. Okay? This is a definition of the kind of programming that Marx talked about calling defensive consistency. And it's actually an idea of which many of us are familiar. A simple case is, well, you know, variables holding code depends on your invariant should be private. Why should they be private? They should be private so that it doesn't matter who you're linked against, you have control over who can pick the object out of that. Okay? So that's a very simple example of the kind of notion that we're trying to capture here. Doesn't matter what you're linked against, we can actually say there are states in the system that can happen, and then in those valid states something will be maintained. Okay? And we can do that, and the example of private is probably the simplest case, even when we don't know who the adversary is. You know, in Java in particular, or in JavaScript with some of the new frozen attributes, for example, we can say this field is not going to be modified. In JavaScript, if you stick something in a closure, and then you build an object within the lexical scope of that closure, someone who gets the object cannot break into it and cannot pull the value out of the closure. Yes?
So I'd be correct in assuming that the composition operator star there is distinctly not commutative. M is in a distinguished position. The composition of M prime and M is such that because M has some, the composition operator has some, we're going to prove some property that M gets to control that M prime does not. Is that true?
Yes.
Okay.
But that doesn't mean that the operator is not commutative.
Okay.
You know, again, if you think about this as JavaScript or Java, the composition operator is almost module linking.
Okay.
And again, you know, in Java at the linker level or at the language level, it prevents private. JavaScript, at least in both of these cases, these are up to reflection or the debugger interface, and in Java, they are up to some.misc.unsafe for those who care. Okay, but you know, if you're not going in and burning through the memory, then it doesn't actually matter which way around you link the Java modules. Private, it's still going to be private.
Okay.
Other questions? Okay, so what do we mean by trust? What do we mean by trust? Well, trust is relative. Okay, so I, you know, may trust Sophia and I trust Mark somewhat less, and some of the rest of you I trust even less. I trust my wife a lot. If I need to pay for something, occasionally I'll just give my wallet to my wife and she'll take the money out of it that I need, or she needs to pay for dinner or something. Whereas I wouldn't do that to many of you for obvious reasons. So here we have trust being relative to a configuration, to some object, and a policy specification. And the important idea which actually applies when I'm giving anyone my wallet, or even when I'm giving anyone my credit card, and is crucial to our notion of trust, is trust is hypothetical. And this is why you can't do this kind of work that we're talking about in basically other specification languages. Because built into all the other specification languages is a notion that if an object, you know, you give a specification and you talk about things in terms of that specification, And the design of these specification languages just has built in that things will do what they're specified. That's the entire point. Why would you write specifications when objects wouldn't obey them? That doesn't make any sense in those contexts. That's precisely what we're doing in this work. And this is what we mean when I say, well, trust is hypothetical. There is no trust bit. We can say, and we will say, the thing appears, some object obeys some specification, right? But it doesn't mean it actually does. Okay, it's a working assumption that we will then use to handle the reasoning. And there's no trust bit. If you were modeling in a traditional specification language, you could basically do it by sticking a bit onto every specification. Is this object trusted or not? And, you know, in theory, you could look at the object and see whether it's trusted. Well, the point is, even if you have an are you trustable bit, any object that's untrustworthy is going to say, yeah, of course I'm trusted. Here's the checksum. Of course I'm trusted. You know, this fake euro that I'm handing you, of course it basically looks like a normal euro. That's how it goes. So all we can say is we're going to say, so we can say that some object obeys a spec if, for all policies in that specification, the specification is basically a collection of policies, and starting from some state of the system, from anywhere we can get, this notion of reach is similar to arising before, well, effectively, the object will obey the policy that this in the policy talks about. So that's basically what we mean by trust. We'll trust an object if it obeys the policy. And if we say we trust some object, what we actually mean is there is some specification for which we'll trust this object. We can never actually know whether an object does behave the specification or not. What this does provide us with is language, which we can then talk about in our specifications to say, well, under the assumption that this object, this is where the hypotheses come in, under the hypothetical assumption that this object obeys this policy, something will happen, and under an assumption that it doesn't, maybe something else will happen. So that leads us to this complementary notion of risk. And risk in sense of the effects against which we wish to guard our objects. In a sense, again, in a traditional specification language, if something doesn't obey the policy, we throw up our hands and go home. But that's precisely what we don't want to do in an open system where all the components may or may not be trustworthy. We want to be able to continue execution, which means being able to bound the bad things that can happen. Here's an example of the kind of specifications we write. It's saying something, there's a deal method, which is being called on this to do some kind of deal. We get a result. What sort of things we can say? Well, we can say that for all pursers, if P obeys valid purse, so if every purse in the entire universe is trustworthy, or at least every purse that gets close to us is trustworthy, and its balance in the post condition, or sorry, the post condition. So the balance in the post condition has not have changed. Either, sorry, we say either the purser's balance has not changed, okay, or we say there is some purse here we're going to call BP, and maybe this one wasn't valid. It didn't obey the specification, so maybe it just randomly changed its specification, or somebody else got to it. And the important thing is that a bad purse, BP, was able to get to the purse, a good purse whose balance has changed. Okay. So what we're trying to do here, and this isn't necessarily the, well, I mean, this is the kind of thing we actually end up writing in practice, is we do this thing using these purse objects, and the question is what purse objects have changed afterwards? Well, if the objects are bad, if they don't obey purses, then we give up, because we don't know what they could do. But if a good purse object has changed, down here, sorry, if a good purse object has changed, then there must have been a bad purse that could get to them. Okay. So I want to do this and then hand over. So this is the escrow agent, where, to the example we put, the idea is we want to have a buyer and seller who want to exchange some goods for money. Okay. You can almost think of this as some kind of synchronous procedure call where the buyer wants to give some arguments to this procedure call, and the seller eventually wants to return the result. We'll talk about buyer and seller, because the point is that the buyer doesn't really trust the seller, and the seller doesn't trust the buyer. How do we know that we give the money and we actually get the goods back is the question, and the answer is, well, we'll have an escrow agent, another object that will make the exchange. And if the buyer and the seller don't put up enough goods into the exchange, then we want to stop the exchange. Of course, this gets more fun. The escrow agent doesn't trust the buyer or the seller, nor what we'll call banks. You can think of these banks as generic resources, modeling effectively the goods which are being exchanged. You can think of these as being two different currencies or whatever. And the point of the escrow agent is that the buyer and seller will somehow agree with this and then use the escrow agent to mitigate the risks. So in that sense, the buyer and seller are trusting the escrow agent, but this doesn't mean that the escrow agent trusts a particular buyer or a particular seller, and neither does it mean that an escrow agent is actually trusting any particular bank. Okay, because again, there's no central trusted authority. How on earth can we do this? Well, here's an example. And this is fairly classic. What we do is we create an escrow belonging to the escrow agent, and we put the buyer's money into the escrow. If that doesn't work, then we quit. If it does work, well, we've got enough, hopefully got enough money in this escrow purse. And then we do the same thing on the other side. We make an escrow purse for the goods, in this case lemons, and we try and put the money into the escrow goods. And at this point, let's say the seller doesn't actually front up with the buyer doesn't actually front up with the goods. If there's no success, then we can just move this money back and be done. Okay, that's the essence of the escrow. We've already got stuff from here. Try and get stuff from there, and if we can't get it, we can quit and we can undo this transaction, and then nobody's lost anything. If there is enough money, well, at this point, or rather just at the previous point, sorry, I have to step through all this again, you get to a point where in both the escrow money purse, that's the non-success case. The success case, we have enough in the escrow and money purse, and what happened in one animation there is that as soon as we got to the point where we got enough goods and got enough money, we took them out and we gave them actually to the end clients. All right? So it's really C stages. Get something in here, get something in there, and then when you can see we have managed to sequester enough of both the money and the goods, then we do the swapping. Okay? This is the basic mechanism of any kind of escrow exchange. And there are particular protocols that describe how you do this. So the important thing are those grey escrow purses in the middle, which are these intermediate stores. And they allow the exchange to be undone if there are insufficient goods. And our escrow agent needs to be able to interrogate the escrow purses to work out if it has in fact got the money, if it has in fact got the goods, to decide whether the transaction goes through or not. But the question is, well, where do the escrow purses come from? Where do the escrow purses come from? Well, the agent could have them before the transaction, but no, because there is no central trusted authority. So ideally we want this agent at one side to be parametric across, well in this case, both the goods and the money issuers, and if that seems a bit weird, again, perhaps if you think about a stock exchange or you've just been and seen The Big Short, okay, what we're actually swapping here are CDOs controlled by Lehman Brothers, and Lehman Brothers are the trusted agency. Right? And we don't want to build trusted Lehman Brothers into every damn escrow mechanism. Okay? The seller and buyer supplies the escrow purses. Okay, well, fine, except, of course, once again, the seller and the buyer don't really trust each other. So they would have to agree before the transaction, but the whole point of this is we want to do this transaction in a way that establishes just enough trust for the transaction to go through without requiring everybody to trust each other at the start. This is to establish enough trust for the transaction to go through and then be done. Well, once again, you could ask banks, and you possibly could do it that way, but basically, again, the agent would need to know about all the banks, and not just to know about them, but to trust them. So the option we ended up going with is that the agent asks the seller money to make one, and the agent asks the buyer goods to make one. Okay? And this is the way our protocol works, so that as part of the exchange, the escrow purses are created and then used in the exchange, and they've done that without any additional input coming in from outside. Okay, so you then end up with the code that looks somewhat like this. And you can see here that we're saying seller money.sprout. I think this is where I need to apologize for the font damage. And which has the seller money making this escrow money purse. And then in the same way around, the escrow goods purse, okay, it's being made by the buyer goods. So that gets us the escrow purses, and then we should be able to get through the escrow code. The last thing I'll talk about is, oh, well, does this work, basically? It has this particular version, and the code is available in the full papers. Buyer and seller, blah, 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 blah. Well, the important bit here, again, is the escrow agent doesn't trust the buyer or seller, and the escrow agent is trying to mitigate the risks. But, of course, what we just said was we're asking the buyer money to create this escrow money purse, and then as we go through, we critically rely on this to do the escrow. Okay, but, well, what happens if, you know, this is effectively a proxy for the buyer. Okay, this wasn't created by the escrow agent, it was effectively created by the buyer, or at least the buyer's purse, which acts for the agent. So what happens if this was completely devious, and actually, where did we create it from? No, we created it from seller. The argument is still the same, whichever way around this is. This one is devious, this one can take more money from the buyer than it should. Okay? Or it could take as much money as the buyer gives it, but then tell the escrow agent, actually, no, that buyer didn't give me any money. At which point the transaction, the escrow agent, following the algorithm, would presumably go on and abort, or if we're really unlucky, would abort in such a way that we got to keep all the money. So those are the risks, and in those kind of cases, you know, this wouldn't work. And this, again, this comes back to where I came in. If we really can't know very much about the escrow money purse because it was created by somebody we don't have control over, effectively, escrow money is in M prime rather than M, well, how much actual damage can it make if you manage to subvert this? At which point, and I'm running slightly late, I get to hand over to Sophia.
Thank you. So please, first of all, thank you to Mark and Daniel for hosting me, and thank you for coming. If there are any questions, please ask. What I'm going to talk about is the second attempt to the escrow agent. I will show you how we can make the escrow agent safe, but also how we specify it and how the whole logic will work to help. So the summary is that we will be extending the remit of the purses, that not only do they do the transaction of the money, but they can also do authorization. If the purses, the purse objects, the blobs that we have seen in the diagrams before, when they report true, when they are satisfied, then we know that the purse that they were collaborating, transacting with, is also trustworthy from their point of view. And so this is the first point. And the second ingredient is that now we will add an extra phase to the protocol so that there is an authentication phase, and then which is followed by the real transaction. So first of all, we spoke about purses, about valid purses, about extending the remit. What does it look like? So there are 4 ingredients to the specification of a valid purse, 4 criteria that a purse, an object must satisfy in order for it to be considered a valid purse. The first has to do with this method of depositing. So a valid purse has got a method deposit that takes 2 arguments, purse and amount. And we have not mentioned this so far, and Gilad will be particularly happy today. We're assuming a language without types. So this is called purse because we are expecting it to be a purse, and this is called amount because we're expecting it to be some sort of number, but there's nothing that enforces that statically. And the result will tell us whether the transaction, whether the deposit was successful. If it says yes, then what it means is that this argument is trusted to be a purse, that the receiver considers this to be a trusted other purse. There were enough funds, and the transfer did happen. On the other hand, there is the other case where the result is false, and in that case, either this purse argument was not trustworthy, or there was not enough funds, and in both cases, the transaction will not have taken place. Then there is the other operation, which is called sprout. This you could call new if you were not Mark Miller, but sprout is much more flowery. And so what it means is we are asking a purse to create another purse of the same trustworthiness. And in the process, nobody else is affected. These operations also have got the guarantee that nobody else is affected, but I didn't have enough space to put it on the slide. There's a fourth part of the policy, and this is not attached to any operation, it's an invariant. And it says you cannot affect the balance of the purse unless you have got access to the purse itself. So there is no some ambient structure that you can go and modify. You have to get to the purse in order to change the balance. So there are three ingredients to this specification. First of all, the functional properties, which talk about under what circumstances does the transaction happen, and what is the meaning of the result, and what does it mean to create a new object. There are the elements that talk about trust. For instance, here the successful report after a deposit means that the argument is trustworthy. Unsuccessful, it might not have been trustworthy, we don't know. And the sprout gives me a trustworthy purse. And the third ingredient is risk. And the risk is described here in this policy that says your purse is not at risk unless somebody has access to it. And moreover, these operations do not affect anybody else. As an interesting side remark, Mark explained to us yesterday that his initial specification and initial idea of the purse is slightly different, and a successful deposit did not imply that the argument is trustworthy, only implied that the transaction took place. But through, as he said it, a constructive misunderstanding of his meaning, we could develop this version of the escrow. So this is the specification of the purse. And now I want to give you a bit more detailed view of what the policy means. So the first policy is when the deposit is successful, what do we know? There is the functional part of the specification. So what we know is that the balance of the purse before the operation took place, this pre-subscript is pretty standard in pre- and post-conditions. So before the operation took place, the balance of the purse was greater than the amount, and after the operation, it is the same as the balance before minus the amount. And similarly, the balance of the receiver will have been increased by the amount. So this is the way to describe that the transaction took place. The next part of the specification has to do with trust. So it says, now we know that the argument purse obeys the specification of valid purse. And the last component is risk. And it is related to what James showed you at the beginning. So we know for all P's, which stands for purses, and objects O, if P is a valid purse and O is an object, then first of all, we know that the balance of the purse will not have been affected by this operation. The balance of the first purse before the operation and after of the operation will be the same. And moreover, any object that can access the P, the particular purse, after the operation could access it before. So that means we do not leak accesses to purses, and that is essentially in order to make sure that the escrow cannot go and mess up purses. Cannot mess up purses. We will see an example of this later. So another point to consider is that we have got conditional trust. If we trust the receiver of deposit, and he says yes, if the result is true, then we know that the argument purse is trustworthy. There is not a bit or some structure that we look at in the heap. It only depends on what other trustworthy objects tell us about each other. And the other policy I want to show you is the last one, which talks about risk, and it says the balance cannot be affected unless I had access to the purse. So that is an invariant. Every purse that obeys a valid purse, and for every object, an object can only affect the balance of the purse, can change the balance of the purse if it has access to it, and otherwise it cannot. So the balance is protected in some way. So we are talking here about necessary rather than sufficient conditions. In standard Hoare logic specification, we are talking about sufficient conditions. So if I have access to the purse and I call the transfer, the deposit method, then I will affect its balance. Here it is in the opposite direction. If I was able to affect the balance, then I had access to the purse. Okay, so now let's have a look at the code that uses these more robust purses, or knowingly more robust purses. Again, we have got a purse for the buyer's money and a purse for the seller's money. And what we want to discuss is only how we go about establishing the risk. It is these extra phases that I spoke about earlier. So in the first step, we are asking the seller money to sprout a new purse, which we call escrow money. So since this one is the result of sprouting this one is trustworthy if this one is trustworthy. So if the seller money obeys valid purse, then escrow money obeys valid purse. In the second step, we make a zero deposit from the buyer money to the escrow money. So if the escrow money says true, if it is happy, and the escrow money is a valid purse, then we know that the buyer money will be a valid purse. So there is a chain of reasoning of trustworthiness. And the rest is going to be another two zero-sum deposits, which finish the chain. And in the end, what we will know is that if the buyer money is a valid purse, then the seller money is a valid purse, and the other way around, because of the chains that go like that. If anywhere in the meantime we discover that the result is false, if any of the purses complain that the transaction was not successful, then we know that one of the purses was not trustworthy and we exit the code. Okay, so this phase is about establishing trust, and when we reach that point, we know that those two are of the same trustworthiness. We do not know that they are trustworthy. They could both be rogue or they are both good. But the other question is, if during any of those transactions, one of the purses was a rogue purse, could it go and steal some money? So what is the risk to which I'm exposing the good guys if just one of the guys was bad? Because if we exit anywhere here, then one of them is good and the other one is bad. And then we want to make sure that we have not exposed the good guys to risk. So the next question to consider is, what is the risk that is involved during this phase of establishing the trustworthiness? So we need again to consider the same code as before, but now we are not thinking about trust, we're thinking about risk. At this phase, what we can establish is that for all purses which are valid purses, for all P that are valid purses, their balance will not be modified unless the seller money could access the purse before the call to the escrow, and the seller money was a rogue purse, was bad. Why do we know that? We know it because there is this other, the fourth policy of purses that says you cannot affect the balance unless you had access to the purse, and because we know that the Sprout method does not have access to anything else except the seller money. So accessibility cannot increase in any way. So if there was anybody who was not trustworthy, if there was any effect to the balance, then it has been done through somebody who had access already before the call, and therefore we have not increased the risk. There is similar arguments that go throughout this, these four steps. So I don't want to go into detail how these arguments go, but the reasoning is similar. And in the end, what we know is that for all purses, their balance will be unmodified, or either the seller money purse was rogue and it had access before the call to the escrow, or the buyer money was rogue and he had access before the call to the escrow. So we have quantified the risk. And now the full code, and I'm not going to go through it, is we do the same kind of authentication as we did for the money purses. We do it for the good purses. So this is the second phase, and in the third phase, we do the same transaction as we saw when James was talking, where we are now only considering whether there is enough money and enough goods. So at the end of this phase, what we know is that everybody is of the same trustworthiness, and we know that we have not modified anybody's balance unless some of the rogue guys had access to the affected purse before the call to the method. Right, so now we want to consider the specification. How do we describe the guarantees that this method of the escrow gives us? So the method we are calling the method D, and I'm assuming, just in order to simplify things, that there are local variables that describe the money purse, sorry, the buyer's the buyer's money purse and the buyer's goods purse and the four purses are arguments, and M and G stand for the amount of money to be transferred and the amount of goods to be transferred. So we have got four cases in our specification. The first case is that after after the call to deal, the escrow reports true. He says success, wonderful. And we know that both the buyer and the seller are good. They have given good purses to the escrow. In that case, what we know is there were sufficient money and goods. Everybody's good. The transaction took place. And no other purse is affected. So this is the first case. The second case is the result is false and the buyer and the seller are good guys. In that case, we know there were insufficient money and goods and no other purse is affected. So far we have been dealing with everybody's good. The third case is the result is false and either the buyer or the seller are bad, but not both. In that case, no purse is affected unless one of the malicious participants had access to it before the call. And the fourth case is the result is true and both the buyer and the seller are bad. In that case, no purse is affected unless one of the malicious participants had access before the call. So these are the four cases. And as we said earlier, James and I were surprised, and then Mark was also surprised. So that's wonderful. Why? The deal method is not as risk-free as we had expected. There is a little risk that is associated with the method, namely, if one of the malicious participants had access before, now that we call a method on him, he can go and create some havoc. And moreover, and more importantly, if the result is true, then this does not mean that the arguments were good, nor does it mean that the transaction did take place. So we have no way of knowing whether the transaction took place, unless, of course, I am one of the participants. So if I am the participant and I know that I have given good purses to the deal method and the result is true, then I know, of course, that the other participant was also good and the transaction did take place. Okay, so last point is the Hoare logic. I'm going to go briefly through some of the formalism that we developed in order to be able to prove adherence of the code to this specification. So first of all, about Hoare tuples. In general, Hoare logic consists of tuples of that kind. There is condition P, some code, and the condition Q. And the condition P is a one-state assertion. It talks about this one state. Condition Q talks about two states. So Q is assertion like P dot balance minus P dot balance pre equals amount. So it can talk about entities that are observable in both the state before and after the call. And what this Hoare triple means is if I execute this code in a state that satisfies Q, P, then after execution of the code, when I finish, I will reach a state where the difference between the state before and after is described by Q. But we extended the Hoare triples and we made them into a tuple where there is one more element, a Q prime, and what it says is if the initial configuration satisfies P, then the final configuration will satisfy Q. Sorry, I would like to go through it. So the final configurations would satisfy Q, and quite formally, in terms of what we have been describing earlier, if I know I'm in a configuration kappa that satisfies P, and I execute it and I get kappa prime, then I know that the difference between kappa and kappa prime will be described by Q. So far we are with standard Hoare logic, but the extra ingredient is this Q prime, which is an invariant, and it says all intermediate configurations will satisfy Q prime. So the extra thing that we know is that in all intermediate configuration, kappa triple prime, double prime, that can be reached through execution of the code in the configuration kappa will be satisfying Q prime. So this is what we need in order to be able to argue preservation of balances, for instance. We need to know that in all intermediate stages it is impossible to change the balance because nobody had access to the pairs. And we need to strengthen the tuples with one more ingredient. So once we have done this, let's go back to method call. The first rule is the rule that James already showed at the beginning of the talk. So if we call a method M on receiver X and argument Y, what do we know? Well, if we know that X obeys the specification, and the specification says that for a method M, the precondition is P and the postcondition is Q, then, and if we know that before the call P holds, then we know that after the call Q holds. And I need to do this renaming here where I'm replacing this for X and parameters for Y. This is just in order to do an adaptation to the particular call. So nothing new here, but there is something new, that something more that we know when we make a method call on a receiver about whom we know nothing. So what we know is that accessibility cannot grow randomly. So this is back to connectivity begets connectivity. So if after the call you can access V, then we know either you could access it before the call, or the arguments, the receiver and the argument could access you. So either the receiver or the argument could access you, and either the receiver or the argument could access V. So we have got a situation where one of or both the receiver and the argument could access the two elements, and therefore they have manufactured the connectivity. And this is an important ingredient to have, because we want to be able to argue that the deal method does not leak references, and we need such a knowledge in order to obtain that, and we need the knowledge of not leaking references in order to know that we have not affected the balances of the purses. There are a couple of structural rules. I think I will just skip them. And the rules for framing. Here is another rule. So there are two rules that talk about any kind of code, so they are always applicable. The first rule is pretty standard, and it says if the footprint of a code is disjoint with the footprint of some property, then I know that the property is preserved. So if the property P prime holds before the code, then it will hold after the code, and it will also hold during execution of the code. So this is standard, and it has been around for the last 20 years. This one is more interesting and more useful for us. So what it says is, if it's an invariant of the code that in order to affect some property, in order for an object U to go and affect some property P prime, U needs to satisfy Q prime. And if I know that during execution of the code, no object satisfies Q prime, then I know that the code preserves P prime. And this is the rule that we needed again in order to be able to argue that we are not, during execution of the deal, we will not be affecting the balance, because in order to affect the balance, we need to have access to the purse, and nobody has access to the purse. So that allows us to argue about code that we might even know nothing about, because we might have restrictions about who has access to things, who has got the property to prime. Right, summary. So we have introduced the concept of may access, may affect, and obeys. These are hypothetical predicates in the sense of quite often we cannot directly observe them, but we establish them indirectly, and they are often conditional. Like, as we said, that if we know that the seller is trustworthy, then we know that the escrow is trustworthy, and then we know that the buyer is trustworthy. So there is this chain of argument. We have expanded the Hoare tuples so that there is an extra component, which are the properties that are being preserved, and we have new Hoare rules. In future work, we want to deal with concurrency distribution. These are things that we hope to be doing very soon, at least if we can put the man hours, the person hours into the work. Because of other constraints, we want to look at framing, example encapsulation, examples, lots of such things. And I, at least, was very surprised that the concept of encapsulation is not something that is buried in the programming level. It's something that crops up all the time in the specifications. As soon as you want to write more sophisticated specifications, you need to make the distinction of what is within a data structure and what is without. So what we have shown is that we can reason in the, about code in the presence of other code, which is untrusted or unknown. We believe that it is important to do that. We have shown the ingredients of this work, but in particular, we need to specify not only what will happen in terms of necessary condition, but also what will not happen in terms of, what will happen is about sufficient conditions. If I know something, I've got a precondition, then the code will establish a post condition, but we also need to think about what will not happen. What are the necessary conditions for something to happen? If I don't have access to something, then I cannot modify something else. So that concludes the talk. We would be interested, of course, to hear your opinions or questions. Thank you. Yeah.
Can this logic be used to work backwards from some kind of violation of trust to work backwards to a set of possible causes for that, or does it diverge? Does it blow up?
I think I would like to rephrase.
Sorry,
Sorry.
go ahead. Yeah, please go ahead.
I would rephrase what you said. I think the logic could do the following. It could say that if such and such happened that is not supposed to have happened, then perhaps I can argue who was the cause of it, who was not trustworthy. But violation of trust, because trust is not is only about potential behavior. It says about how does the object behave in the future. So the concept of violation of trust is not directly reflected in our system. You agree, James and Mark?
So I think just using the specific example, I think there is a way in which we have a positive answer to this question, which is, let's say that one of the participants finds that they lost their money and did not get the good. Then this analysis tells that participant what the possibilities are about who the bad guy is and what they might have done. Now, there's several different possible explanations. It might be that the escrow agent was dishonest. It might be that one of the banks was dishonest. But it says, it takes some of the choices off the table, which is, if the escrow agent was honest and the banks were dishonest, that even if the counterparty was dishonest, you know that you're not going to lose your money but not get the good, that somebody else had to be dishonest.
Indeed, yes. So, for instance, if to say a little bit more on that, if you lost your money, you had used the escrow agent, and then you know that one of the other participants was bad, but not only that, that he had access to you before the call, so you can find the reasons. And I had never thought of this backwards reasoning, but yes, you can do it and think it's important. Yeah.
Sorry, got that. Excuse me.
Okay.
Can you return to the slide that has the chain of the zero transaction? That went by somewhat quickly for most of it, at least for me. I don't know about the rest of it. Right.
So shall I complete it?
Yes. So I guess the question I had on this, the question that came to my mind, and I'm not sure it's well formed, is how is the result valid? How do we know that this result is valid even if the value wasn't 0? How is it independent of the value of the particular value of the argument?
I think you are asking how can we write this, the implementation of, how can we write an implementation that would satisfy valid pairs? Yeah? How can I write some a class with a method deposit, and so that if the result says true, then I can vouch for the other pairs.
Yes. Yes. What's exactly? How does that come to bear? to come to be? That's
just a clarification. Are you asking how one can implement a purse that obeys the specification?
I'm asking how. So this sequence,
Yeah.
right, establishes the bidirectional relationship.
The bidirectional conditional relationship.
Right, and I guess the question that came to mind was, how do we know that that's true even if the second value is the argument is anything other than specifically 0?
Okay.
Or what do you? I can phrase it differently. Is it possible to write this in such a way that I can spoof you, like, yeah, it works for 0, but not for other values?
Yeah, absolutely. You can write a purse that works completely faithfully for 0, and then for non-zero steals the money.
Okay.
And the point of the conditional reasoning
right.
is the escrow agent is never in a position to know that a purse does not behave in that malicious way.
Okay.
But in the formalism, what we're describing, we would describe such a purse as not obeying the spec.
Okay.
And what we're saying here is that the chain of implication here is conditional implication of if this purse obeys the spec, then that purse obeys the spec.
I see.
So when we reach that point, even though everything has said fine, all we know is that they are of the same trustworthiness. We don't know that they are
exactly. Okay, thank you. I see.
Yeah, good behavior is not evidence of trustworthiness.
That's right.
Yeah.
And this works because there is a clause in the specification of the purse that explicitly says you can make that reasonable stuff. So you could imagine purses and has that doesn't have that.
No.
So I wonder how does aliasing affect the made assets? Like in the in the actual implementation, aliasing could be very messy, right? So for the specification is
good
so
point.
how do you say I may assess a field or a region, or so what's the element?
I think yes is an answer to that question.
Just clarification first. We said at the beginning that we do not consider aliasing. If you are referring to that. What we meant is we do not consider the situation where buyer money and escrow money are aliases of each other. And the reason we do not consider that is just because it means, so we assume by fiat they are not aliases of each other, because if we were to consider that, then we would have to write much, much longer specifications, and that wouldn't bias anything. Now, the may access predicate is defined that in the heap there is a path from one object to another object. So aliasing, of course, would affect that.
So it's an object tree. So I cannot I cannot assess anything that can point to the thing that could be harmful.
What we said is, if you are referring to that, I cannot modify the balance of a purse unless I have a path to that purse. So if there was a global data structure that had got a sequence of bits, and the fifth bit, the fifth entry was the balance of a certain purse, and the sixth was the balance of another purse, then I wouldn't have that property, because we could go and modify balances without having the identity of without knowing the identity of the purse.
So in reality, the specification could be much more complicated for aliasing, etc.
So this specification does take care of aliasing, yeah? Well, it does not say explicitly. Perhaps we should go and look at what the specification says. This one, yeah? So it says an object may affect the field balance of a purse P. So may affect means it is able to call some method, and this method as a side effect will modify the value of this term. And it says if somebody can affect the balance, then he should have this object that can affect the balance. He should have a path that leads to that purse in the heap. So if the purse object is here, and he has got the balance field, and there is another object O who can somehow magically modify his balance, then he needs to have a path that leads me there. Sorry. There must be a path that can go through other intermediate objects that gets me to this object here.
No. Yeah, so one of the things reducing the case explosion of aliasing is may access is reflexive. For all O, may access OO.
Thank you.
Thank you. All right, so thank you very much. It was very interesting talking here. Thank you.
Thank you.
Thanks for having us.
Bye, Sean.
You only say bye after they log out.